Okay. Are there any questions before I begin? No? I posted the assignment number 5. Also, the solutions to all the 4 assignments are up on the model. And assignment number 3 is marked on its back. 4 is with the TA, 5 is with you, and the exam is with me. Still, that's just the status. So today what I want to do is complete the development of the mass transfer problem, 1D problem, and then begin looking at 2-dimensional fluid mechanics problem. So we're going to go back to section 1 of Burstable and Lightfoot after we finish looking at this mass transfer problem. So in the last lecture, we looked at 1-dimensional free convection problem, and we can see the similarity between the models, whether it's fluid mechanics, heat transfer, or mass transfer. And the important parameter there is the Grashof number, that is a ratio of the buoyancy force to viscous force that governs the velocity field. And the velocity profile we are able to obtain as a solution to the governing momentum equation after simplifying it for the 1-dimensional case. In the current assignment, the problems are all from heat transfer. They're all variations, meaning if I did a pipe flow, I would ask you to do a parallel plate geometry, which is what we did for force convection. Then if I did a parallel plate, like we did in free convection, then I ask you to do in cylindrical coordinates. So it's only the coordinates that's different, but the mechanics of solving it is exactly the same. All the problems are from the end of the chapter in Burstable and Lightfoot. So I've given you the problem number reference as well if you want to look at it. So it's basically to make you go through the mathematics of developing the solution. Physically, conceptually, it is the same problem that we have seen in a different geometry. Okay. Now, then we looked at the general mass transfer problem of mass transfer to a liquid in a falling film. And the complete model is governed by, complete 1-dimensional model is governed by this equation that you see here. But that has in it the convective velocity Vz, which is given by this profile that you see there. Okay, so the velocity is not a constant, but has a parabolic profile for a falling film. And the coupling is from the fluid mechanics to mass transfer, meaning fluid mechanics affects the mass transfer, but not the other way. And so it's a balance between the convection in the downward direction versus the diffusion in the perpendicular direction. Okay, and that is what the equation captures. So this is the diffusion in the x direction. That term is the convection in the z direction. And we saw a set of meaningful boundary conditions. Boundary conditions come from understanding the problem. And here the problem is that at the entrance, the velocity is, the concentration is 0. At the interface where the mass transfer is taking place, the concentration is the saturated concentration. And at the other end, there is no mass transfer. It's an insulated, impermeable wall that you have here. So there's no mass transfer. So the flux is 0. That is the general set of boundary conditions for the differential equation, which is fairly difficult to solve because we need to use separation of variables for a situation where the velocity itself is a function of x. It's a quadratic function of x. So we said we are going to simplify the problem further by saying that we are going to look at sparingly soluble or weakly soluble gases in the liquid, in which case we can say that the concentration doesn't penetrate all the way into the wall, but it is always going only to a small distance. And over that distance, we can assume that the velocity profile is fairly constant. So that makes this term that you see here as a constant. Then the problem becomes exactly the same as the impulsively started plate. Mathematically, it has exactly the same form. So the solution is the same, and that solution is given by the error function. So instead of velocity, we have the concentration, and instead of kinematic viscosity, we have the mass diffusivity. So only the language changes, physical terms, but mathematical language remains the same. So we get an expression for the concentration profile, and then we can, once you have the concentration profile, you can use it in Fick's law to get the flux, and once you have the flux, you can integrate the flux to get the mass transfer rate, that is how much of material in kilograms or kilomoles per second material is absorbed. So, and we saw that this is also called the Higgby's penetration theory among the mass transfer theories. And then we started looking at the second example, which is a slightly more complicated example, where we have mass transfer from the solid side. So we have a dissolving solid into the liquid. And the reason that it is a bit more complicated is because we cannot assume that the flow is constant. We have to assume that the flow is linear. Once again, sparingly soluble system. Okay, so the concentration is not penetrating all the way to the free surface, but only to a small extent. Then we can linearize the quadratic profile, and once it's linear, we can still solve it in a simpler way than solving by the separation of variables. And that's where we stopped. So we went through the linearization process, and instead of the velocity as a quadratic function, we have the velocity as a constant times y, and the constant is known in terms of the properties of the fluid. Okay, so here a is known and y is the distance measured from the wall. So now the mass transfer is from the wall, and Ca naught, once again at the wall, is the solubility limit. Okay, what is the maximum amount that a solid can dissolve into the liquid, and the entering fluid is free of that solute. And as you go farther away from the solid liquid interface, in an asymptotic sense, the concentration is 0. And what we have here is, once again, a similarity transformation that is possible because we don't have a natural length scale. And so we have gotten rid of the natural length scale. There is a natural length scale in terms of delta. Delta is the thickness of the film. But for sparingly soluble systems, it looks like it's an infinitely long film. It's not a thin film anymore. It's a thick film from the point of view of the molecule that is diffusing into that liquid. So that's why we replace that condition by y going to infinity asymptotically. Okay, and when we say that we can define, for example, Ca divided by Ca naught as a dimensionless concentration. We can divide both sides by Ca naught, and the numerator becomes a dimensionless number. Okay, because Ca naught is a known concentration, and this will become 1. The boundary condition will become 1. And you normalize it that way. Again, in the current assignment, there is an exercise where you need to go through the scaling to put them in dimensionless form. Okay, but that means the remaining variables in that equation can be grouped into a dimensionless variable, and that is given by eta equals y multiplied by a divided by 9 dAb z to the power 1/3. Now, 9 is thrown in there as a constant. That makes the calculations simpler later. But the important point to notice here is that when you take this y to the denominator here, you get y cubed effectively in the denominator. And here you have z and dAb, okay? And a also on the other side. So eta is defined as y times a divided by 9 dAb z to the power 1/3. Okay, so the power 1/3 comes from visual inspection, but if you want to do it proper way by letting these exponents be unknown factors, you can also achieve the similarity transformation for even more complicated problems. Here it's a fairly simple one by inspection. Now, we have combined two independent variables. What are those independent variables? Y and z. Y divided by z to the power 1/3. That is a combination that is going to make this equation into an ordinary differential equation that you see later on. Okay, but A and DAB are there just to make it dimensionally consistent. Now, how do we convert that PDE into ODE? Again, through the standard process. The process would be take the term dCA dZ and write it as dF d eta times d eta dZ. Chain rule. Okay. So dF d eta is just F prime, and d eta dZ you need to obtain from here by taking the partial derivative. So there is a good page of algebra involved in there in calculating all these partial derivatives and plugging it on the left hand side and on the right hand side. Once you do that and simplify, you will find that wherever you had y and z on both sides, they will cancel out, and you will get this following ordinary differential equation. Now you can see why we put the 9. That makes this into 3, a nice number here after you simplify that. There is a good one-page algebra involved in there. Okay, and it's just a matter of taking the derivatives, substituting onto the original equation, and cancelling y and z wherever that they appear, and you'll get this ODE. Another thing that we need to do, so we have converted the PDE into an ODE, and so we have the similarity transformation, but we also need to make sure that we have converted the 3 conditions that we have here, the inlet and the boundary conditions, into 2 consistent conditions, because we have only a second order ordinary differential equation. We can impose only 2 conditions. And of course that happens automatically, because when you take the first condition, for example, okay, y at z equal to 0. When z equal to 0, what happens to eta? Because z appears in the denominator, when it is 0, eta becomes infinite. So what this will tell you is that this condition will transform to f of infinity equal to 0. Now if you take the second condition, that is at y equal to 0, that means eta is 0 is equal to 1. Okay, and the third condition will become y is infinity, but z is some finite number. So y is infinity means eta is infinity from this one. Okay, so once again that infinity is equal to 0. So 2 of the conditions are identical. That means we have been able to consistently transform that into 2 second order ODE with 2 boundary conditions that are consistent with the 3 conditions and the partial differential equation that we had before. Any questions so far?
So we always keep y raised to the first power, not any other power than that, and keep the constants to arbitrary, like maybe 1/3, not like y cubed to.
Yes, you could do also, because you are defining this function eta equals a function of y and z. So it's your choice. So if you do this, for example, a constant times y cube divided by z, that will also result in succeeding transforming that PDE into an ODE. Okay, the ODE may look a little bit more complicated, but the transformation would be successful, because what is key is that the ratio, that y cube and z. Okay. So the next question is, how do I solve this second order ordinary differential equation? It is a variable coefficient, meaning one of the terms that multiplies here is dependent on the independent variable eta squared itself. Okay, but it's fairly easy if you let that g is equal to, for example, df d eta. Define a new variable g equals df d eta, the same trick that we did before, okay, in the Stokes problem. So then it will become dg d eta equals minus 3 eta square g. So I've taken this to the right hand side. So I'm writing it as minus 3 eta squared df d eta, but df d eta is g. Now this is separable. Okay, so you can separate that and write it as dg divided by g equals minus 3 eta squared d eta. You can integrate both sides. Okay, then here you will get log g. On the right hand side, that integral doesn't exist. So we just have to keep it as, sorry, this integral exists. So it is eta squared, so eta cube over 3. And so the 3 will cancel out, so you will get minus eta cube plus an integration constant, which I'm going to call this as log c. Okay. Now take logarithm of all sides, and you can write this as g equal to CE to the power minus eta cube. But g is nothing but df d eta. This is what we defined g to be. Okay. So you have to integrate one more time. Okay. And that's how you get the solution for f. So f is equal to integral of e to the power minus eta cube d eta plus another integration constant C2. This doesn't have an analytical integration for it. So just like we had e to the power minus eta squared d eta, we just defined it as an error function. Okay, so we can in your textbook it just leaves it as an expression that you see here, integral of e to the power minus eta cube d eta. Now there are two integration constants here that you need to find out by imposing the two conditions. And when you do that, you get this as the final result. CA over CA naught is this integral, which cannot be evaluated except numerically. You can always evaluate it numerically. Okay? Divided by 0 to infinity of e to the power minus eta squared d eta. Now, that is going to be a number. Remember, what do we mean by that integral? That integral, like if you plot, for example, e to the power minus eta cube against eta, what will that curve look like? When eta is 0, e to the power 0 is 1. Okay, so it's going to start at 1, and as eta increases, what's going to happen to it? You'll go to 0, but it'll go to 0 very rapidly because you're cubing it, and it's negative. Okay, so the denominator is the area under this whole curve. That's a constant, that's a number. And that number is given by, this is called a gamma function, but it's basically a constant. Okay, it evaluates to be something like 1.7 or something like that. But there is also a function called a gamma function. The gamma function evaluated at an argument of 4 over 3 turns out to be this integral. Now, what is the numerator? The numerator is the integral from some eta value all the way to the end. So it's the area under that curve from eta. So the numerator is a function. It's not a constant. It's a function because it depends on eta. One of the limits depends on eta. So you choose a value of eta that fixes a left boundary and integrate it all the way from there to infinity, and that gives you a value in the numerator, and that will be the CA over CA naught for that value of eta. Okay, any questions? The math is only incrementally more complicated than the error function solution because it's still the same steps are involved. Once you have the composition, you can plot that and you can take the gradient of that, the derivative of that, and evaluate it at a particular value, for example, at y equal to 0, and plug it into the fixed law, and that way you can evaluate what is the flux of the material that is dissolving from the solid into the liquid phase at the boundary, at the solid liquid boundary. That is fixed by y equal to 0. Okay? That means you need to take the derivative of this function with respect to y and then put at y equal to 0. Okay? And that simply means apply the chain rule. dc dy is dc d eta dy. Since I know eta as a function of y, I can take the derivative. So I can take all these derivatives and evaluate them at y equal to 0. And what I get is, once again, an expression for a flux that depends as 1/3 to the power of z. The rest are all constants. Okay. Previously, when the velocity profile was flat, we had 1/2. Okay, but now we have cube root of z and cube root of dab, diffusivity, when the velocity profile is linear near the wall. And the total flow, once again, is calculated as an integral of the flux over the cross-sectional area. And so you plug in this expression that you have, and an integral of z to the power negative 1/3. You can easily do that. Okay, so plug it in there and carry out the integration, and you get this expression. That is the practical expression that we are interested in, answering the question of When I put a pure solvent on the top and expose it to a solid surface that dissolves into it, what will be the amount of material that I'll get in the liquid at the bottom? Okay, and that is the total length that you see. So over that length of the liquid height, how much of material will I get? And that is answered by this expression for WA. Okay, so variations of these kinds of problems you should be able to handle, and current assignment is exactly giving you that kind of an opportunity to work on the variations.
I have a question.
Yeah.
Does it have something to do with the velocity of the fluid?
The velocity of the fluid, of course. Good question. Where does that expression appear here? I guess I kind of deleted the last lecture, so I started off with this. This is the velocity. Okay, so the fact that the velocity is varying linearly has already been taken into account in the integration in the y that you see here. Okay, the other part is a. The velocity, the slope of the velocity is determined by a, and that depends on rho and g, the thin film result. Okay, so the effect of the velocity is certainly influencing the solution, and that is appearing in this term a. Okay, so that net final rate should depend on, that's a good way to look at intuitively afterwards. What should it depend on? It should obviously depend on the diffusivity, it should depend on the solubility, it should depend on the total area. Okay, W times L is the interfacial area between the solid and the liquid, the depth being perpendicular to the bore, and L is the length along the liquid film. And it should also depend on the velocity profile, particularly the velocity gradient, which is A in this case. Okay. Any other questions? Okay. So there are lots of such problems one can solve, okay, in different geometries, in cylindrical geometries, spherical geometries, etc. And we have just kind of opened up the basic ideas behind it, and you should be able to handle all the variations. Now we're going to go back and look at two-dimensional flows, flows where we have at least two velocity components. Okay, so something like this, the velocity vector. The postulate on the flow is that there are two velocity components, v1 and v2, and they depend on x1 and x2, two directions at least. The third component is 0. Okay, when that happens, the continuity equation is not trivially satisfied. You have to have the continuity equation reduced to this. Because v3 is 0, the third term drops out. Remember, the continuity equation, if you remember, it comes from del dot v, which is dvi dxi in index notation. Okay, and when you expand it, you will get dv1 dx1 dv2 dx2 plus dv3 dx3 equal to 0. The last term drops out by the postulate, but the first two terms have to be balanced. In fact, it's something that you used in your one of the earlier assignments. This is the local continuity equation to find out v2 if v1 is known. Okay, because this must be satisfied at every point in your flow domain. Now, in solving such problems, we introduce this notion of a stream function. Okay, and we define the stream function. So it's a definition. We define by these two equations. That is, v1 is d psi dx2 and v2 is minus d psi dx1. So psi is called the stream function. What is psi? Psi is some function which is a function of both x1 and x2. Okay, it's a scalar function, which is a function of both x1 and x2. And when you take its derivative with respect to x1 and put a minus sign, it will give you what v2 is. And when you take the derivative of the same function with respect to x2, it will give you the component v1. Okay. Now, why do we define it like that? I said this is an arbitrary definition. It's really not arbitrary. Why do we define it like that? The advantage of defining it like that is when I take the definitions and plug it back, for example, for v1 here, and for V2 there, I will see that the continuity equation is automatically satisfied. You can see that in the next step. So you have d dx1 of V1. But V1 is d psi dx2 according to the definition. Okay, and then you have the next term, which is d dx2 of V2, but V2 is minus d psi dx1. I'm just plugging in. Okay, and then psi is a continuous function of x1 and x2, so I can write this as the second derivative, d square psi dx1 dx2. Okay, that is, this term will simplify to this, and this term will simplify to this, d square psi dx2 dx1, with a minus sign. So we introduce the minus sign deliberately so that I get a minus sign here, and that is automatically equal to 0 if psi is a continuous function of x1 and x2. So the idea is that there is some function called a stream function. We should give it a physical interpretation, and we will do that soon. But mathematically, we define it according to this equation. V1 equals d psi dx2 and V2 equals minus d psi dx1. And once we do that, it automatically satisfies the continuity equation. So I don't have to worry about satisfying the continuity equation if I choose to work with this variable psi instead of V1 and V2. So in all the two-dimensional problems, we will see that instead of working with V1, V2, and P, these are called primitive variables, natural variables in which the Navier-Stokes equation is expressed, V1, V2, and P. We'll get rid of that and express the problem in terms of stream function, and we'll get a single equation, a scalar equation, still a partial differential equation that we need to solve. Okay, but we don't have to worry about continuity equation, and we can get the velocity field from the definition, from the defining equations here. Okay, any questions on that? So that's a simple definition of a new function that we are introducing. What is the physical meaning? Can we give it a physical meaning to this stream function? And how can I visualize it in my mind? The way to see the physical interpretation is we recognize that psi is a function of x1 and x2, right? So if there is a small change in delta psi, d psi, this can occur either by changes in x1 or changes in x2. So I can use the chain rule to write the total variation in psi as partial d psi dx1 times dx1 plus partial d psi dx2 times dx2. That's just chain rule, because the nature of the stream function is that it is a variable that depends on both x1 and x2. Then I use the definition for what is d psi dx1. D psi dx1 is the same as minus v2 from the definition of the stream function. Similarly, d psi dx2 is the same as v1. Okay, so first chain rule and then use the definition, and so we get this equation that we have here. Okay, that d psi is equal to minus v2 dx1 plus v1 dx2. Now, along a constant streamline. Now, what is a constant streamline? A streamline is one which is a curve in space. Okay, so if this is x1 and this is x2, I can draw a line on which psi is a constant. The value of the stream function is a constant. Do you understand what I'm meaning? This is the physics that we are trying to understand of this mathematical function. Okay, so when I say that I can draw a contour, you all understand what I mean by that, right?
Psi is a constant in space.
Psi is not a constant in space. Psi is actually a function of both x1 and x2. So if I have to plot the variation of psi with respect to x1 and x2, how would I do that? Let me go to the blank sheet. Okay, so I can create a graph like this where I have x1, I have x2, and on the third axis I plot psi, because psi is a function of x1 and x2. So if I give you a value of x1 and x2, you can plug that in and calculate a value of psi. Okay, so that's going to give you at this point a point in the third axis. So I can, now let me ask you the thing. What would be, if I have to plot this, I give you a function psi. In fact, there is a little exercise that is coming later on. How will this surface, I give you the answer. How will this function look like? It'll be a surface. It'll be a hill, for example, a mountain. Okay? So you have your latitude and longitude, you have the two coordinates, and you have a mountain, and the height of the mountain at that latitude and longitude kind of represents this kind of a function. So when I say that I'm plotting a contour of a constant psi value, what do I mean by that? So on the xy plane, I drew a line, and I said that is a contour of a constant stream function. So I can have many such contours. For example, psi 2 and psi 3, etc. Each curve is a curve on which the value of psi is a constant. How would I get that? All I have to do is imagine that you have a mountain here and you're cutting the mountain across at a constant value, constant height. So the edge of that mountain would trace a curve. You project that curve onto the x1, x2 plane, and that will give you a curve. And that is what is called a contour. The contour is a line on which the value that we are plotting remains a constant. MATLAB, Mathematica, Maple, all of them have these contour routines. And I'll show you how to use them later on. But at this stage, what I want you to understand is that this stream function is a function of two spatial variables, x1 and x2. And one way of representing that is as a three-dimensional surface, okay, in a three-dimensional graph, or in a two-dimensional geometry in the x1, x2 plane, a projection of that where you're cutting the mountain at different levels. Each cut gives you one curve. And on that curve, the value of psi will remain constant. Okay? That's the physical geometrical interpretation. So if I draw a curve like this, this curve need not be closed. Okay? It can just be a curve over a region that I'm interested in, and that curve represents a streamline. It is called a streamline, and on which the stream function is constant. If the stream function is constant, what is d psi? 0. Okay? That means if I take 2 points that are close to each other, there is no variation in their stream function values. They have the same function values. So d psi is equal to 0. So by setting d psi equal to 0 in this equation, I can rearrange that equation as v2 over v1 equals dx2 over dx1. Okay? So that means if I take, for example, 2 points here, I'm just going to exaggerate a little bit. That is delta x2, this is delta x1. What is delta x2 over delta x1? That is the tangent, right? So I can draw a tangent to that curve at that point. So the tangent to the streamline gives you the velocity vector. Okay, so a streamline is a beautiful representation of the flow, because if you have a whole series of streamlines like this, you know the tangent locally gives you the velocity vector. So you know in which way the fluid is flowing. So if I put, for example, a die to mark how the fluid is flowing, a die will trace the path of a streamline under steady flow. Okay, so these are all under steady state conditions. Any questions? Now that's a concept. I want to make sure that you guys get it. So we introduce stream function as a mathematical entity that satisfies the continuity equation automatically, but it has a beautiful physical interpretation, and that is along a constant streamline, the tangent vector gives you the direction of the velocity field locally. Okay? And another even more beautiful interpretation of that is, if I have two streamlines that are certain distance apart, psi and delta psi. Okay, so this is a streamline, meaning the value of the stream function is constant on that. But this is another streamline on which the value of the stream function is a different constant, and that difference is delta psi. That difference is delta psi. Okay. Now, this delta psi is a direct measure of the flow rate. Okay, so if any liquid that gets in through this cannot, by definition, can a velocity vector be like this? Because we just said that it has to be always tangential. So there cannot be a cross flow. The flow cannot cross a streamline. Okay? And so whatever fluid that enters here must leave there. Okay? What does that mean? So suppose I have two streamlines that are like this, and the flow is in this direction. What can you say about the velocity in this region versus the velocity in that region? Will the yellow region velocity be high, or will the green region velocity be high? Right, because it's the same amount of fluid that is flowing through a narrow region, right? So the velocity, so that if you plot contours of streamlines, you can immediately visually tell that in this region the velocity is much higher than in that region. Okay, so qualitatively you get a picture of that, and mathematically we can show, and that's what this exercise is about, that the net value between this is a measure of the flow rate. That is psi2 minus psi1. The difference between two stream function values is equal to Q. How do we do that? Again, it's physical interpretation of a mathematical equation. The mathematical equation is the same one that we started off earlier. That is d psi is equal to minus v2 dx1 plus v1 dx2. We already got that in the previous page. So I'm going to integrate that between two streamlines 1 and 2. And because the left-hand side is a total derivative, the integral of that is simply psi2 minus psi1. The right-hand side, I'm not going to integrate with any specific function, but just do the interpretation. For example, if I have the velocity in the x direction crossing this in the left direction, okay, because the flow is this way, so the x component must be pointing this and y component must be pointing up. Okay, so that's why this gets a minus u. And when I integrate that between the two, my integral of minus u dy and then integral of v dx, that should be, what is the velocity times the cross-sectional area? Flow rate, right? So this gets the interpretation that it is a net flow evaluated as sum of two integrals, whatever that is entering in the x direction and whatever that is entering in the y direction. So the physical interpretation for this entire term, because it is velocity times area, but area in this case is perpendicular to the board, we are taking unit length. So two-dimensional flow, right? So dy times 1 is an area. Similarly, dx times 1 is an area. Okay, so that's why we replace this by, or interpret that as the flow rate. So that shows the difference between two streamlines is directly a measure of the flow rate, and that's another nice feature of it. Here is your think, pair, share exercise. We haven't done that in a long time. Sketch that streamline for me. Yeah, I've given you the function. This is a solution to some problem we will see later on, but right now I'm just telling you that the psi is given as u r squared sine 2 theta. U is a constant, and r and theta are in cylindrical coordinates, two-dimensional cylindrical coordinates. How would that streamlines of that function look like? How can I plot that? Take a minute to think about it and try to sketch it. remember, what we want is to plot, when I say plot streamlines, that's what I want you to think about. I told you what a streamline is. A streamline is a line, a curve, on which the value of psi is a constant. Streamline is one where it's a curve on this graph, and I've set up the coordinates for you. Okay, theta is measured like this, r is measured like that. The equation of u is a constant. So it's a curve on this. On the curve, psi must be constant. On theta must change. So think about how you would write a program to plot it for you. Of course, MATLAB SSL does it. You just throw this expression, MATLAB, Mathematica, they will all plot the graph. But I want you to kind of think through what does it mean? What am I plotting? How can I generate such a graph? When you're drawing a curve, what do you need? You need a set of a pair of points, coordinate points. So if I give you a series of coordinate points, r and theta values, on which psi is a constant, you can just connect all those curves, points, and that's your curve, right? So you need to generate such a curve, such a set of points. A set of points r theta, a table of points on which psi is a constant. So there are some streamlines that you can draw by inspection. For example, psi equal to 0. Streamline where the stream function is 0. What would those lines look like? When is sine theta 0? Sine 0, right? So you can say, for example, that this is a streamline. On this streamline, oops, on this streamline, psi is equal to 0. Why? Because theta is equal to 0 for all values of r. Okay, so r will keep changing on this curve, but as long as theta is 0, it is 0. Sine is 0. Sine 0 is 0. So the stream function is 0. What is the next curve that you can think of where stream function is 0? The vertical one, right? When you put theta equal to pi over 2, because you have 2 theta, so it becomes sine pi. Remember, the sine function, you need to remember that, goes like this. So it's 0 here, pi, 2 pi, etc. So sine 0 is 0, sine pi is 0, sine 2 pi is 0. Okay, so this would be a stream function with psi equal to 0. What are the pair of values of r and theta? R is any value, theta is 0 in this case, and in this line, r is any value, theta is pi over 2. And what will be the next one? This one. So these are some streamlines, and remember, the flow cannot cross a streamline. Okay, to generate other streamlines is going to be a little bit more tricky. Okay, how could I do that? For example, if I want to plot a streamline that corresponds to psi equal to 1, how would I go about it?
R equal to 1 and theta is equal to pi by 4.
R equal to 1 and theta equals?
Like initially pi by 4 because that will be pi.
Okay, and what will you get out of that?
It will be when theta is equal to pi by 4, it will be on that line, and R is equal to 1 line.
Right. So you could pick r equal to 1 and theta equal to pi by 4, but what is the stream function value there? You can calculate that. It'll be u. Okay. So there is a streamline passing through this with a value of u, you know that. But I need to get, that's a very good starting point to plot the next value of the streamline. Okay. So you are now chosen to plot a streamline with a value of u. Now what I need to do is, okay, I'm going to fix the value of u on the left side and then pick various values of theta, and for each value of theta find the value of r. Do you follow that? So that's exactly what a computer program will do. So now I've plotted psi equal to 0 everywhere. Now according to her suggestion, I want to plot a streamline where psi is equal to u, not 1. That's convenient. Why? Because r equal to 1 and theta equal to pi over 4. I picked that. Okay. So I need to now put psi equal to u and pick a value of either r or theta. You can do either one. Okay. So for example, if I pick a value of theta, a line along that, I need to solve for r. I put in theta, I put in psi, and I solve for value of r. And I might get a point there. And I take another angle, put the same value of u, and solve for theta. I might get another point there. And I take another angle, and I get another point there. Take another angle, I get another point there. That's how I construct that streamline. So I connect all these points, and I will get a streamline psi is equal to u. I can do this for any value of psi, psi equal to 1, psi equal to 2, psi equal to 3, etc. And what you will find is that I get a series of streamlines like this. And this is called an impinging jet problem. So what happens is, if I have a water that is impinging on a wall, okay, so the water is coming in this direction, and here is a wall, and the water jet is impinging on the wall, and the way that it will divert is given by the stream function for a planar geometry, not a circular cylinder, but you must have a planar jet because it's a two-dimensional problem. Do you get an idea of what a stream function is? Because that's essential before we're going to use this very frequently and very fluently. So I want you to understand what a stream function is. Okay, and of course the tangent to the stream function will be the velocity vector. So the thought process of constructing it is simply the solving that equation repeatedly, where you pick a value of psi, you pick a value of theta, and solve for r, just to take the square root function, right? So you take a lot of points on the r theta grid, and then connect all the points that have the same value of psi, and that will give you the streamlines. Any questions on that?
Have we fixed the value of psi and the value of r?
Solve for theta, you can do that too.
But which one is more useful or convenient?
Both are useful in the sense they will give you the result. Which one is more convenient? In this case, solving for r is more convenient because it's only quadratic. You're taking the square root of it. When you solve for theta, sine theta can have infinitely many values that will satisfy that equation. So you need to pick the ones that are within 0 to 2 pi or 0 to pi if you want the upper half, right? So you need to kind of do some checking on that. Whereas square root is just plus or minus. And radius can never be negative, so you can take the plus always. Okay, so the way that you would do that in Maple is with this command. Start Maple and say with plots, it loads all the plotting routines, and then there is a function called contour plot. Okay, I want you to tell me what have I done here. This is a piece of code. Can you understand it, decode it, so that you can kind of build and use on your own? What have I done there? It's the same problem that I've given you. Because Maple requires it in Cartesian frame, I just switched from r theta to xy coordinates. So r square is simply x square plus y square, and theta is tan inverse y over x. And I made u as equal to 1 because u is a constant. In this case, I've just picked. And what does this mean? X from minus 100 to 100. Y goes from 0 to 100. And I'm specifying the range over which I want the contours to be plotted from 0 to 100. And then I specify how many contours do I want. So I plot 20 contour values. Okay. So these are all the decisions that you would make when you're plotting that. So you tell the program, and it just generates a graph instantly for you. Now, the next concept that we need to understand is vorticity. As you already talked about a vortex. What is a vortex? Here is a mathematical introduction and a physical intuition about what a vorticity is. Vorticity, again, is a mathematical function that we introduce in a particular way. And we will see the definition, mathematical definition later, but let me introduce the physical intuitive explanation of that. So if I have a coordinate system x1, x2, and I have a fluid element here, and the fluid element has a velocity in this direction. Okay, so it is as if the fluid element is rotating. It is rotating about this axis. Okay, so a sense of a rotation. What is the intensity of rotation? We want to define that. We want to capture that, and that is what vorticity is. So physically, it turns out that it is twice the angular velocity of local angular velocity of a fluid element that is undergoing rotation. Okay. So in this particular case, the V1 component, which would be this, the horizontal component, and V2 will be the vertical component. So if R is the radius and omega is the angular velocity, then R omega sine theta will be the horizontal component, and which you can write as R omega times sine theta. Now sine theta is the same as x2 over R. These two triangles are similar. Okay, so this is x2, this is x1. So we have a coordinate point. We are focusing on this fluid element, which is a distance of x1 and x2. Okay, so sine theta here is x2 over R and cos theta is x1 over R. And then we are decomposing that velocity into v1 and v2 from the angular velocity. The angular velocity is what? Omega times this velocity component. Okay, will be omega times R. Correct? This velocity. And that is being decomposed into a horizontal component, which is omega times R times sine theta, and a vertical component, which is omega times R times cos theta. Okay, so that is where this is coming from. The velocity of the fluid element that is rotating at an angular velocity omega is omega times R, and then you decompose that into two parts. Then use the fact that sine theta is the same as x2 over R, and cos theta, sine theta is the same as x2 over R, and cos theta is the same as x1 over R. So the R will cancel out in both places. Okay, and what you get is minus x2 omega, x1 omega. That's an estimate of the two velocity components when the fluid is rotating with an angular velocity of omega at a distance x1 and x2 from the origin. Okay. So in the limit of this shrinking to a point, you can take the limits and you can rearrange this as omega equals minus dv1 dx2. But from this equation, you will get a different result. That is omega equals dv2 dx1 in the limit of delta x, delta x1, delta x2 going to 0. So we get two different answers, seemingly two different answers for the angular velocity. Okay, so we say we're going to take the average of these and define that as your angular velocity. Okay, 1/2 dv1 dx2 plus, but remember, one of the definition has a negative sign in there. So it's not, where is that? Like here. Okay, we're just taking the average. We're adding them to taking the average, but one of them has a negative sign. And that's why we get the negative sign here. So that's one definition from a physical interpretation, that this vorticity is twice the angular velocity, and it's a measure of the local sense of rotation at every point in a fluid element. Now the strict definition, mathematical definition of vorticity is this curl, and it is indicated by omega, and it is the curl of the velocity del cross v, and in index notation it is eijk dvj dxi. So the vorticity is a vector in that sense. So there is a sense of rotation about x-axis, a sense of rotation about y-axis, and a sense of rotation about z-axis. So if a fluid element is rotating in an arbitrary direction, I can decompose that vorticity into three components. Stream function was a scalar variable, whereas vorticity is a vector quantity. It is a curl of the velocity vector, and you have, it gives you the rotation about three principal axes, if you like. Okay, and for 2D flows, what happens? For two-dimensional flows, where you have V1, V2, and 0, the third component is 0, then it turns out that there is only one component of the vorticity that is not 0. All the other two components will be 0. Meaning, if I have x1 and x2, and there is a flow like that, there will be rotation only about the x3 axis. Because there is no flow in the x3 direction, there cannot be any rotation about the x1 axis or the rotation about the x2 axis. Is that clear? Okay. Those are two important quantities, mathematical quantities with a physical interpretation, that we will be using a lot in two-dimensional analysis. Okay. One is the concept of a stream function, the other one is the concept of vorticity. Now, we are going to go back to the full Navier-Stokes equation and do a scaling analysis to see how we can get rid of this term. So far, we have been getting rid of that term by assuming the flow to be one-dimensional, rectilinear flow, where that assumption knocks off that term identically. And then the equation is linear, we can get a solution. But once you go into the two-dimensional flow, that term will not be 0 identically. But we have to argue identify when will that term be small compared to other terms. So this is the scaling analysis. So this is your continuity equation, and this is your full Navier-Stokes equation. What is PD here? Dynamic pressure, because I don't have G explicitly there. I'm interpreting that as a dynamic pressure. Okay. So I'm going to introduce certain scales. Scales are known quantities. For velocity, for example, there is a known velocity. In the case of a Stokes flow, the velocity of the moving plate. Okay. And there is a known length scale L. And the ratio of L square over nu has the units of time. So you can use that as a time scale in problem where there is no natural time scale. But in problems where there is a natural time scale, you can choose to use that as your scaling variable for time. What are the problems that will have a natural time scale? You're oscillating a plate. The frequency of oscillation will be a natural time scale that you could use. Okay? And for pressure, this is not so obvious, but it turns out that that quantity rho nu u over L has the same unit as pressure. And it involves only all the known quantities. Rho is known, nu is the kinematic viscosity which is known, u and L are given, the scales for the velocity and the length. Okay? So choosing these as our dimensionless variables, so I'm going to define V tilde as V. V is a dimensional variable divided by u. So that makes V tilde dimensionless. X divided by XL makes X tilde as dimensionless. So T tilde is dimensionless, P tilde is dimensionless. Okay? Now I'm going to take the Navier-Stokes equation and plug in for the Navier-Stokes equation wherever I have V, this term. When I have V, I will replace this by V tilde times U. Wherever I have X, I will replace it by X tilde times L. Wherever I have T, I will replace this by T tilde L square over nu. And similarly, wherever I have P, I will replace it by P tilde rho nu u over L in the continuity equation and in the momentum equation. Now, this is called sometimes a naive scale analysis because we are assuming that the velocity is the same in all three directions. That is not true. So later on, when we do the boundary layer theory, we will realize that we need to actually refine the scales a little bit more detail. And that was done by Prandtl. But this is basically Stokes analysis for Stokes flow past a cylinder, past a sphere, etc. This result is extremely useful. I'm sure you have all used it in undergraduate classes where you're determining the settling velocity of a particle or a rise velocity of a bubble. Those are all determined by solving this particular problem. So we are going to take a couple of lectures in going through the solution to this problem in fairly great detail. Still, there are a lot of intermediate steps that I would miss it up. So you need to make sure that you fill that gap that I'm going to point out what needs to be done, but you need to fill it in. So in the next assignment, I'll give you a similar problem where you get a chance to work through all the details. Okay? So in the continuity equation, if you take this equation, substitute, for example, for v tilde times u. So I get v tilde, but u is a constant, so I can take it outside of the derivative operator. Okay, and then what is delta? Delta is d dxi. That's a gradient operator, right? So when I put that in dimensionless form, in the denominator, what would I get? Wherever I have x, I must replace by x tilde. So this will be the same as d dxi tilde multiplied by 1 over L, right? And that's how I get this del to be del tilde, dimensionless form of the gradient operator, and I get a L out of that. So I get u out of the velocity and I get L out of the del operator. Do you understand what's happening? Because I'm going to go through this very quickly later on. So you better understand it here, and I'm going to say the same thing happens, and you will see all the dimensionless terms popping out. Now, in this equation, u is not 0, L is not 0. These are known scales. So my dimensionless equation becomes delta tilde dot u tilde equal to 0. So that's the dimensionless form of the continuity equation. Okay. When I do that to the momentum equation, that's where you need to pay attention. Now, let me try to use the color code as much as possible. So v gives rise to u, okay, and t gives rise to L square over nu when I put that into the momentum equation. Okay, so where is this? What is this giving me? U square. Okay, and what is this giving me? 1 over L. Delta gives you 1 over L. Okay, and then in pressure, that P tilde, actually I missed the tilde there. I think you should put a tilde there. P tilde, and then you have delta, which gives you L. And 1 over rho exists already in the momentum equation. You go back to the momentum equation, you'll see the 1 over rho is there already. Okay. And the last term is v gives rise to u and del square. That's a Laplacian operator, right? So that will give rise to L square in the denominator. Okay, and nu already exists. So now I have made all the terms dimensionless, but every term has a factor in front of it, which is consisting of constants. Okay, and the actual terms are dimensionless now. What is the reason for making these dimensionless? Of course, first they are dimensionless. The other one is the magnitude of them will be of the order 1. Okay, because whatever the velocity is, I'm scaling with respect to u. Now, u, for example, in a tornado could be 150 miles. So when I scale them up, all the scale velocities will be of the order of dimensionless unit 1. Okay, whereas in a microfluidic device, that u, the mean velocity, could be of the order of so many micrometers per second. Okay, then once again, I'm not dealing with extremely small numbers. When I scale it up, I'll get numbers that are between 0 and 1. So the idea is that every one of these terms that I see here are of order 1 because I have put them in dimensionless form. So the relative magnitude of each of these terms is determined by the pre-multiplying factor. So if a factor in front of that is going to be large, then inertia is important. If another term in front of the viscosity is very large, viscous term is important. So I can understand relative importance of various terms. That is the main reason for doing this scale analysis. So multiply throughout by L squared. This is just a manipulation divided by u over nu. And so here you have L square u over nu. And everything that you see in that line is just a multiplication by a constant term, L square over u nu. And then you simplify the terms. Okay, and here you will notice that L square and L square cancels out, u and u cancels out, and nu and nu cancels out. So this whole term becomes just 1. The pre-multiplying factor for the transient acceleration term becomes 1. And what happens to this one? So one of the L will cancel out, one of the U will cancel out, so you will have UL over nu. What is that? It's a dimensionless number, right? All of them should be dimensionless, but that will be the Reynolds number, right? Remember, nu is same as mu over rho. Nu is the kinematic viscosity, which is defined as mu over rho. Now, what happened to here? Rho u nu, and then you will have L square 1 over L 1 over L. So that also becomes of order 1. And in here, the same thing, u nu, that cancels, and L square cancels. This is also of order 1. So it's as if by magic we got all the terms to be 1 except one term. That term multiplies the inertial term. Okay? So when you look at the final form of the equation, we are defining Reynolds number as UL over nu. And that is known. U is known. The velocity scale is known. The length scale is known. The property of the fluid is known. Okay? So this is the only term that we can control, because we control U, we control nu, we control L. All the other terms are of order 1. Any questions on that? Choice of scaling, or how we went through to make it dimensionless? In one of the assignments, current assignments, you're supposed to do this scaling, dimensionalization. Now we argue that as R goes to 0, not exactly 0, but approaches 0, that is for very small Reynolds number flows, this is what the whole film by G.A. Taylor is about, low Reynolds number flows. Okay? And the low Reynolds number flows, even though this term is not exactly 0, it gets multiplied by a small number. So we can assume that this is small. Not 0, but the entire inertial term is small. And when you do that assumption, the equation reduces to this, where the initial term has been dropped by the justification that even though it is not 0, it is small. And the question then is, are there flows where Reynolds number is really small? Is this a practical situation to study? And it turns out that it is. There are a lot of situations in nature where Reynolds number is extremely small. Once again, this is a good time for those who have not seen the film by G.A. Taylor to go back and take a look at it. Because all the phenomena that he describes in physical world are in this domain, the domain where the Reynolds number is small, not 0, but small. Okay? And that equation is called Stokes equation. The previous complete equation is called Navier-Stokes equation. This is called the Stokes equation. Have we changed the nature of the problem when you do this? Okay, it's still viscous dominated flow. What was the troubling problem with the Navier-Stokes equation? The non-linearity in this equation, in this term. V dot del V. V appears as a product. That's non-linear. There is no way we can solve that analytically. So we first looked at situations where the term was spontaneously dropping out. These are one-dimensional flows. And there are a lot of one-dimensional flows in nature that are useful. Okay? And then we are now looking at two-dimensional flows where the term cannot be eliminated but can be assumed to be small and dropped out because of that. And then we can solve the remaining equation and look at the flow behavior. Okay? And that will be the so-called low Reynolds number hydrodynamics. There are two excellent books. One is by Happel and Brenner. They are both are chemical engineers. I think all of them are chemical engineers. The other one is by Sainte Kim and Carrella, microhydrodynamics. The entire book devoted to solutions of these two equations in the creeping flow limit. This is called a creeping flow limit or a zero Reynolds number limit. Any questions on that? That scale analysis is actually valid for three-dimensional flows as well, because we never said anything about the nature of the velocity field. Okay? We just took the full Navier-Stokes equation and did a scale analysis on that to show that the inertial term gets multiplied by RE, and RE is the physical interpretation for that. It is a ratio of inertial force to viscous forces. Why? Because RE is the length times U times rho divided by mu. Here we have written it as nu, but mu is mu over rho. So here is your mass times velocity term. That is your inertia. Okay, so it's a ratio of the inertial force to viscosity in the denominator. So when inertia is small, Reynolds number will be small. That means I can neglect this term. Okay, so that we have done for a general three-dimensional case. But we're going to go back to 2D case to be able to solve even the Stokes equation. So we are now focusing on a very simple problem, and this is solved not in such an extensive state in your book. So we'll go through a little bit of detail, more detail than what is given in your book. The problem is the following. You have a flow of a fluid that is approaching a sphere. Once we do a sphere, you can do a cylinder and other things as well later on. So the flow is approaching with a uniform velocity. The sphere is fixed. Okay, so the streamlines are going to come like this and then be deflected like this and come down. And the streamline that comes straight here will be like this. So this will be a zero streamline, for example. So this is why we introduced the idea of a streamline. So this is how the velocity profile is likely to look. And we need to show that in fact it does by solving the Navier-Stokes equation. Sorry, the Stokes equation, okay, because we're dropping the initial term. So this is the problem. Physical problem is flow past a single isolated sphere in an infinite medium. Okay, and if we know what the velocity is, what are we interested in calculating? Why would we want to solve such a problem? I think it's too late in the day. Right, so you want to know what is the velocity profile near the boundary. Why would you want to know that? Yeah, I heard the word somewhere. Force. Solving any problem in fluid mechanics is to find the relationship between the velocity and the force field. Okay, so we want to know, for example, think of this. Suppose there is wind blowing and I have a tiny spherical bead of polyethylene. I leave it. What happens to it? It will just be blown away, right? So what would I need? I need to apply a force to keep it stagnant at that place. So what I need is, what force should I apply to that sphere to keep it in place so that the liquid just flows around it, but the sphere is stagnant. Okay, that force is called the drag force. So it's the force that is exerted by the fluid that is flowing past this particular sphere.
Is this a general situation or is it laminar or turbulent? Because there is a wave and
In general, a problem like this, when I have a sphere and I'm blowing air or liquid past it, could be laminar or turbulent. Okay, the physical situation can be laminar or turbulent. But what am I going to solve for now? Not only laminar flow, called creeping flow, low Reynolds number flow. Reynolds number going to zero. The solution that I'm going to obtain after a lot of hard work, and this was done by Stokes almost 150 years ago, right? After a lot of hard work in solving this equation, is going to be valid only up to a Reynolds number of 1. If the Reynolds number is greater than 1, that solution will not be valid. And later on, people have improved through series expansion. We will see some of those ideas as well. But you can take this problem, put it in COMSOL, and get the drag force at Reynolds number of 400. Okay, that's the beauty of a package like COMSOL, because it solves a complete Navier-Stokes equation. Okay, but we are going to solve only the Stokes equation, so we are solving only for laminar flow, but creeping flow, very low Reynolds number laminar flow. Okay, but the same problem physically is meaningful at all Reynolds number, but we need to go back and develop different techniques for solving them. Okay, the next question to ask. So we are after solving the Stokes equation to get the velocity gradients near the surface. And once I know the velocity gradients, I know the stress distribution, I know the forces. I can calculate what is the net force that is exerted on that particle by the flowing fluid. And this is important in a number of situations. If you have, for example, a skydiver, you're designing a parachute. What happens? What is your goal in designing a parachute? Land safely. Land safely. So that immediately tells you a bound on what is the impact velocity. If he impacts it at 100 miles per hour, gone. Right? So you need to make sure that you bring down. So you need to apply drag. You need to increase your drag. How do you increase your drag? You design your parachute so that you have a large area and it offers a lot of resistance, a lot of force. Okay, and so in undergraduate course, you might have done these kinds of problems where you design a parachute, but the drag coefficient is given to you. For a parachute, the drag coefficient is this. Then you can set up a simple equation between the force and the velocity. Okay. Here we are going to solve for that relationship analytically for this particular problem. The next thing that we need to understand is this concept of axisymmetry. I think we have already talked about it. But mathematically, you need to understand what that means, what I've written there. dv d phi is equal to 0. Now, this is a sphere. I said it's a sphere, right? So what would be the natural coordinate to use? A spherical coordinate, right? So I need to have theta or, and then the third coordinate would be phi, which will be going around this axis. Okay. Now, if it's a perfect sphere and I have a flow that is approaching that sphere, as I go around this axis, what would you expect? Around this axis, just take that plane and then rotate it. Will the velocity profile look different in different planes? You would expect them to look the same, right? And that's what we are saying here. That in the phi direction, there is no gradient, there is no change. And that is what we call axisymmetry. And it is the axisymmetry that is going to reduce this into a two-dimensional problem. The Stokes equation, a two-dimensional problem. What is this state? V dot I phi equal to 0. There is no component of the velocity in the phi direction. Okay? So the velocity is pointing only in the r and theta direction, nothing in the phi direction. And that's what makes it into a truly two-dimensional problem. Okay, so it is a steady flow. This term drops out. And there is no variation in the phi direction. And the phi velocity itself is 0. Okay, so the continuity equation reduces to this in spherical coordinates. So you need to find this expression at the end of Bursthaver and Lightfoot, okay, or in the formula sheet that I have. You have to pick the right one and then start cancelling it, and you will get the simplified continuity equation like this. Remember, in Cartesian frame, what would have this been? dv1 dx1 plus dv2 dx2 equal to 0. But because it is spherical coordinates, we have ddr of vr. But these are the scale factors, the metric coefficients that introduce these particular terms. Similarly, you have dd theta with respect to v theta. But once again, these are because of the curvature in the other two directions, the theta and phi direction. We get these terms. But it's basically the same thing. Why am I pointing this out? We knew how to introduce the stream function for Cartesian frame to satisfy the continuity equation automatically. The question is, can we come up with a definition for stream function in spherical coordinates, or can we take the definition that we have in Cartesian frame and transform it, do a coordinate transformation to find out what it is in the spherical coordinates? You can do it either one of the ways, and what you will find is that, where is it? I have a whole page going through. I guess I was going to talk about okay, I guess I probably jumped ahead. That is the definition of the streamlines, stream function in spherical coordinates that will automatically satisfy the continuity equation. Okay? And we will come back to this later on because we're almost out of time as well. So we need to do the same thing for the momentum equation, subject to that condition that it is two-dimensional flow. That v velocity vector has Vr as a function of r theta, and v theta as a function of r theta, and v phi is 0. Take that and substitute into the Navier-Stokes equation. We will simplify the two momentum equations. And we'll see how to solve that in the next lecture. So we'll stop there for a moment. Okay. Any questions? The next lecture is also going to be pretty mathematical as we go through this difficult problem to solve. Okay.